AMD Ryzen Threadripper processors are absolute monsters in performance, almost keeping pace with the fastest desktop chips under lighter or single-threaded loads with over 5 GHz boost clocks, whilst also managing some absolutely mind-boggling all-core speeds under heavier loads. But with a 350 watt TDP, alongside the option to increase that further with Precision Boost OVERDRIVE, getting the most out of these processors without throttling or overheating issues requires great consideration when it comes to cooling. Today, we will be going over a variety of different cooling options for Threadripper, including our own range of all-in-one liquid coolers and a few high-quality air coolers to compare against. Firstly, we have our standard liquid coolers, designed primarily for use in standard desktops with Intel Core or AMD Ryzen processors, but can still effectively cool the Threadrippers to some degree, thanks to the TR5 SP6 mounting ring. Many current AIO coolers available from other manufacturers also share this style of smaller, rounded cooling plate, and claim to be suitable for use on the Threadripper platform, so we wanted to include these to test those claims. Secondly, we have our latest coolers, designed specifically for the Threadripper platform, with large, square-shaped copper bases which cover the entire heat spreader. This ensures all the heat gets transferred directly into the cooler, specifically where the liquid is running through, rather than heating up the screws at the edge of the plate. And finally, we tested a few of the Threadripper-focused air cooler offerings, including 4U compatible Noctua and Supermicro coolers, and the desktop Noctua NH-U14S. The Supermicro cooler is an older model designed primarily for EPYC chips, but as the current TRX50 socket is still compatible with SP3 and SP6 coolers, we wanted to see if it could manage with these newer, higher TDP processors. We kept our testing procedure very simple, just a single CPU-based blender render of the Cosmos laundromat demo from start to finish, pushing the CPU utilization and boost clocks high across as many cores as possible to provide a consistent workload across our chips. For results, we're looking at the frequency limit, which is what the processor determines to be the upper limit of its possible boost clock, the effective core frequency, which shows the current working frequency of the processor, and the core temperature, which is the average taken across each of the processor's CCDs. In most cases, the frequency limit should hover slightly above the effective core frequency, as the latter takes into account any micro pauses that occur throughout processing. Starting with the 7960X, the results show that the lower core count processors are much more difficult to cool compared to the higher core count ones. This follows on from earlier struggles we had with the 280 watt 16 core variants of the 5000WX series. As every processor in the Threadripper lineup has a 350 watt TDP regardless of core count, on a heavily multi-threaded workload like this, that wattage gets spread relatively evenly across every core. On the 64-core processor, as we'll see later in this video, 350 watts spread across the entire heat spreader allows even our lower-end coolers to maintain a decent cooling capacity as the heat is spread across its entire contact area. The fewer chiplets, the more focused that heat is, causing hotspots that are much more difficult to manage for most coolers. This is where cooling our 24-core processor stumbled. You can see that even our most powerful coolers, designed to cool the entire chip surface, struggle to handle any more than the stock 350 watts, with only our 360mm radiator strong enough to maintain any PBO boost at all at a meager 50 watts. Many of the coolers couldn't properly manage even the base TDP, with noticeable performance penalties across their tests, particularly on the Supermicro, showcasing how important it is to ensure that even if a cooler is socket compatible, it is designed to run with your newer hardware. As we step up to the 32-core processor, the temperatures even out enough for some of our smaller coolers to make a better showing. The U14S air cooler can now maintain a 50 watt boost, and more of our coolers manage to complete the test without severely throttling performance due to heat. All three of our Threadripper optimized coolers outperform the desktop parts. While the desktop coolers were able to manage the stock TDP, both the 240mm and 280mm square base coolers soaked up enough heat to maintain an additional 100 watt boost, and the 360mm going up to 150 watts without throttling. The NH-U14S keeping up with a 50 watt boost shows that a solid air cooler can still outperform a suboptimal liquid cooler. The Supermicro managed slightly better on the 32-core compared to the 24-core, but as expected is now the only cooler that cannot maintain the standard TDP of the newer chips. The 7980X with 64 cores, despite lower all-core clock speeds, has even better cooling performance across the board, with a wider selection of coolers now able to maintain some level of boost throughout our test. Both of our Threadripper optimised 280 and 360mm radiators can hit a much higher 600 watt threshold, though it's clear that the 240mm radiator is the bare minimum, with it being just capable of 400 watts. Though it's here that we start to see the detriment of using the desktop coolers on these chips. The average temperatures don't reach past 90, but the 240 and 280mm radiators suffer measurably as multiple CCDs begin to hit 95 while the rest are running remarkably cool. This leaves the processor throttled down to only 3.6 GHz and cause the test to complete about 5 minutes later than the Threadripper optimised 240mm radiator. The 360mm desktop cooler was able to match the light PBO of the 400 watts that the 240mm got, though was evidently still being throttled with an average 3.8 to 3.9 GHz, compared to the 4 GHz the smaller radiator managed, still resulting in a minor loss in completion time. The Noctua U14S was capable of maintaining 500 watts, and the NHD9 held well at 400. Unsurprisingly, the Supermicro continued to be insufficient, pinned at 95 degrees with a much lower frequency limit than the others tested. While it might be better served in a chassis with multiple high-performance fans pushing air through the case, it's clear that even though this cooler is socket compatible, it should not be used on these higher-end processors. This also applies to the desktop coolers. While they can be useful in a pinch for lower-end models, the lack of a full-size cooling plate means it can't effectively remove the heat from the larger surface area of the chip, making it throttle much sooner than it otherwise should. Given our testing, we would recommend all Threadripper-powered systems use an all-in-one liquid cooler designed specifically for the platform for optimum results. Especially if you're looking to overclock, a properly designed cooling system is necessary to get the best out of it. We build all of our Threadripper systems using our custom AIO cooler with a large base plate. This means our systems offer excellent cooling without the usual maintenance required of fully custom liquid-cooled setups, and allows for maximum performance across all cores by utilising PBO boost. Our Magnetar M64T7 uses our largest 360mm AIO cooler, providing excellent cooling for maximum all-core boost clocks, and our Magnetar 2U R64 has a custom AIO cooler that allows for up to 550 watts PBO for unsurpassed rack mount performance. Info and pricing for both of these and our other desktops, workstations and servers can be found on our website linked in the description. That's all for this video. However, Dan is currently hard at work testing the limits of overclocking these processors using a 1.5 kilowatt chiller. We will be going over the results of these tests in a future video, so subscribe if you'd like to see that. Thank you all very much for watching.